we shall discuss another mean value theorem called Cauchy's mean value theorem. Here also we use Rolle's theorem to prove the Cauchy's theorem. Here in Cauchy's theorem we compare two functions fx and gx. The statement of Cauchy's mean value theorem says if fx and gx are real valued functions satisfying the conditions. The first condition is fx and gx are continuous in the closed interval ab. Second one is fx and gx are differentiable in the open interval ab. And the third condition is gx is not equal to 0 in the open interval ab. That is g dash x, of course the derivative of gx we take, g dash x is not equals to 0 for every x in the open interval ab. Even at the end point, that is g of a is equal to g of b, then also g dash of x becomes 0. That is the derivative of gx becomes 0 for some x between a and b. So the third condition can also be said as g of a is not equals to g of b. Of course, I repeat the third condition, g dash x d by dx of gx is not equals to 0 for every x in the open interval ab. The conclusion says that then there exists at least one point C in the open interval ab such that f of b minus f of a divided by g of b minus g of a is equal to f dash of c divided by g dash of c. Here, for the proof of also, we define a new function hx containing fx and gx such that hx satisfies Rolle's theorem. So let hx is equal to fx minus a into gx, where a is a constant and it is to be determined such that hx satisfies all the conditions of Rolle's theorem. For first two conditions, that is hx must be continuous in the closed interval ab and hx must be differentiable in the open interval ab, fx and gx are continuous in the closed interval ab and fx and gx are differentiable in the open interval ab. So both the conditions of Rolle's theorem for the function hx are satisfied. That is hx is also continuous in the closed interval ab, derivable in the open interval ab. Now for the third condition, that is the value of hx must be equal at the end points a and b. In other words, h of a must equals to h of b. So with this statement or with this equation h of a is equal to h of b, we find the value of constant a. So constant a is equal to f of b minus f of a divided by g of b minus g of a. Let us call this as equation 2. Now with this a value, hx satisfies all the three conditions of Rolle's theorem. That is hx is continuous in the closed interval ab, differentiable in the open interval ab, and h of a is equal to h of b. So applying Rolle's theorem, that is by the conclusion of Rolle's theorem, there exists a point C in the open interval ab such that h dash of c is equal to 0. That means d by dx of hx, or d by dx of fx minus a into gx must equals to 0 at c. And from this we obtain that big A is equal to f dash of c divided by g dash of c. Let us call this as equation 3. Now by comparing 2 and 3, both will represent big A value, that is constant A value. From 3 it is f dash of c divided by g dash of c, and from equation 2 it is f of b minus f of a divided by g of b minus g of a. So we see that f dash of c divided by g dash of c is equal to f of b minus f of a divided by g of b minus g of a. So this proves the theorem. Here we know that if g dash of c is equal to 0, then LHS becomes infinity. So g dash of x is not equals to 0 for every x in the open interval AB, that is the third condition, must be essential. And also if g of a is equal to g of b, then the right hand side becomes 0. The denominator in the right hand side becomes 0. So again the right hand side becomes infinity. And also by the Rolle's theorem, g dash of x is equals to 0 for at least one point in the open interval AB. So we see that this violates Cauchy's mean value theorem. So the third condition, g dash of x is not equals to 0 for every x in the open interval AB, must be satisfied.